Okay, let's go ahead and get started. So I think my computer is working today. Looks like it's working. So administrative announcement. I'm just passing around right now the first problem set. That's going to be due a week from tomorrow. It's all fairly self-explanatory. Yeah, just pass those up to the front when just pass them up to the front when you're done with them. Yeah, so it should all be fairly self-explanatory. Yeah, so they'll be due next Friday. Here you go. Next Friday at 3:30 p.m., just before the colloquium. Please make sure to read the instructions. So turn them into the mailbox that's labeled Physics 610 in the Physics Department mailroom instead of putting them in my personal mailbox, because that's a great way for them to get lost if they go in my mailbox. And don't put them in Scott's mailbox either. They probably won't get lost quite as much if you put them in Scott's mailbox, but you never know. Okay, let's go ahead and start with the physics. So I'd like to continue with our brief review of special relativity and Lorentz invariance. So just to remind you of a few things that we mentioned last class. So when we talk about the symmetries of special relativity, what we really mean is that the equations of motion of the theories of physics that we're going to be studying are invariant under certain changes of coordinates. So you label your points in space-time by a set of coordinates x mu, where mu is an index that runs from 0 up to 3. Its 0 component is just time, and its other 3 components are the usual spatial coordinates. And the theories that we're interested in are invariant under translations, where x shifts by some constant that I'll call a mu. A mu here is another 4 vector. This includes, for example, both time and spatial transformations. And we're also interested in theories which are invariant under Lorentz transformations. That is to say, they're invariant under changes of coordinates where x mu goes to lambda mu nu x nu, where lambda here is a 4x4 matrix that I've written in index notation as an object with one upper index and one lower index, mu and nu both running from 0 up to 3. And I'm using the Einstein summation notation so that this new index here, which is repeated, is summed over from 0 up to 3. These Lorentz transformations include both rotations and boosts. Rotations being those coordinate transformations that mix just the spatial directions, boosts being the ones that mix time with the spatial direction. And the defining property of the Lorentz transformation is that it preserves the invariant interval, or the invariant inner product of special relativity, which is the generalization of the Euclidean distance of Pythagoras to special relativity. So it preserves x mu, where I lower an index here on x by contracting it with the metric of special relativity. So this is equal to x mu, x nu, g mu nu, where g mu nu, the metric of special relativity, is the 4x4 matrix whose diagonal entries are 1, minus 1, minus 1, and minus 1. So here, whenever we have an object with an upper index, we lower it by contracting it with the metric. So for example, x mu is g mu nu x nu, or if I wanted to take this 4x4 Lorentz transformation metrics, I could define lambda mu nu to be, for example, g mu rho lambda rho nu. So here all I'm doing is using my metric g mu nu to lower indices. And likewise, I could use the inverse of the metric to raise indices. So we could define g with 2 upper indices to be the same matrix. It's just the inverse, well, it's just the same as the metric g with 2 lower indices. And then we could use g mu nu with 2 upper indices to raise indices. Okay. So this is an operation that you're already very familiar with in vector calculus. Raising and lowering indices is just the same as Well, it's not even doing anything in vector calculus, because usually when you denote a vector by a set of three quantities, say xi, you mean the same thing when you have a bunch of lower indices as when you have a bunch of upper indices. In special relativity, however, we need to be careful about whether we're talking about lower indices or upper indices. The reason being that, as you can see explicitly from the form of the metric here, depending on whether we have an upper or a lower index, you may or may not get some minus signs wandering around. Okay, good. And as I said earlier, as I said last class, there are two different conventions for the metric of special relativity. You can either have the metric whose components are 1, minus 1, minus 1, minus 1, or the one whose components are minus 1, 1, 1, 1. I'm going to try and be consistent and use the conventions of your textbook, the mostly minus conventions, but I will frequently make mistakes and accidentally use mostly plus because that's the metric that I actually think in. For example, I'm already realizing now that at some point on your problem set I used the wrong signature metric. So extra credit is to figure out where that was. You will get 0 points of extra credit if you figure that out. Good. Okay. So the defining feature of the Lorentz transformation is that it preserves this invariant interval. So x mu mu, which is t squared minus x squared, if we wrote it out in terms of the usual space and time variables. And in terms of that 4x4 matrix lambda mu nu, that translates into the statement that this is what we worked out last time, that, so let's just work it out again. So if you want to calculate this in our primed coordinates, where x mu prime is going to be lambda mu nu, x nu, what is this? Well, this is x mu prime, x nu prime, g mu nu, just writing out exactly what I mean when I lower an index. And then let's write that in terms of the unprimed coordinates. So that'll be x alpha, x beta, lambda mu alpha, lambda nu beta, g mu nu. And this is supposed to be equal to the invariant interval, which you could write as x alpha, x beta, g alpha beta. Okay. So one word of warning, when we're using Einstein summation notation, we can freely relabel indices that are being summed over. Okay. So for example, earlier I wrote the invariant interval up here, where I summed over an index mu here, or where I summed over indices mu and nu here. And I rewrote it down here where I was summing over indices alpha and beta instead of indices mu and nu. Okay. Alpha and beta are summed from 0 up to 3. I could call them whatever I want. I could call them alpha, I could call them beta, I could call them elephant, I could call them whatever I want. They're summed from 0 up to 3. It's just some notation. But it's something that you'll definitely have to get used to as you get used to dealing with index notation. So for example, on the problem set that you're doing, you'll have plenty of opportunities to get used to abstract index notation. Okay. How many people are sort of comfortable with Einstein summation and index notation at the level? Okay. So many of you, most of you. Okay, good. Okay. So why is special relativity useful? Why is this language useful? Okay. The point is that the laws of physics, as far as we understand them, are invariant under translations and Lorentz transformations. And that highly constrains the possible laws of physics. In particular, it means the laws of physics, that is to say, the equations of motion of any dynamical system consistent with these symmetries, can be formulated in terms of what are known as tensors. So what is a tensor? Well, a tensor is a kind of object that transforms in a particular way under a coordinate transformation. That is to say, it transforms in a particular way under one of these Lorentz transformations. How many of you have seen tensors before? Oh my God, where did you see tensors? GR. You've all taken GR before? Many of you have taken GR before. Okay, well then this will be just a lightning review. Okay. For most of you at least. So what is a scalar? A scalar is some function of these coordinates x mu that is a function that depends on the coordinates only in the obvious way induced by the change of coordinates in special relativity. That is to say, if you take this scalar and you want to write it in the primed coordinates, then all you do is just use the formula that relates the primed coordinates to the unprimed coordinates. Okay. That is to say, a scalar is a function not of coordinates of space-time, but only of the actual point in space-time that you're thinking about. And if you just make some coordinate transformation where you use different sets of coordinates to relabel different points in space-time, then the value of the scalar at that point should be unchanged. Okay. That's all that we're writing here. Okay. A scalar is what you usually think of when you think of a function that only depends on a point in space-time. Okay. So a scalar is, of course, the simplest sort of tensor. The next simplest type of tensor is a vector, and in particular what's known as a covariant vector. And that is a set of four quantities, that is to say, four functions of the coordinates that transforms in a particular way when you perform a change of coordinates. In particular, if you write it in the new primed coordinates, so let's write it, then it will pick up a factor of this Lorentz transformation matrix. So let's, okay. So if you think about it, this is in fact nothing more or nothing less than the obvious generalization of what you mean by a vector in linear algebra or vector calculus. So for example, the usual vectors that you see in linear algebra are three quantities that transform under a rotation by a multiplication by a rotation matrix. And all we're doing here is multiplying by the analogous 4x4 matrix in special relativity. And here, of course, the argument changes in the obvious way because as you perform one of these Lorentz transformations, the coordinates that you use to describe a given point in space-time change. Is this clear? Any confusions about this? Okay. You know, sometimes people will distinguish between a 4-vector, which is just a set of 4 numbers that transforms in a particular way, and a vector field, which is a set of 4 numbers associated with any point in space-time that transforms in a particular way. Typically, whenever we talk about vectors in this course, we'll be talking about vector fields. Whenever we talk about a scalar, we'll be talking about a scalar field. Yes, question?
I'm a little bit confused about the new prime versus the new.
Yes.
Why
So,
is it
well, okay. I mean, there's a bunch of different sort of conventions that people can use, notations that people can use. You can either think of a prime as being associated with an index, or you can think of prime as being associated with the letter v in a given coordinate system. So I'm thinking of the prime. I'm thinking of this prime as being associated with with the other coordinate system. So, for example, would it make you feel more comfortable if I put primes there? Okay, I can put primes there. Yes. Yeah. Often, you know, we'll be a little sloppy when the notation. You know, sometimes if the notation is completely clear, I would be a little sloppy and I would leave out the primes there, because you would think of v prime as being the vector in the other coordinate system, and mu is just being the index. Or you could think of mu prime as being a prime living with the index. If that makes you happier, then great. Happiness is hard to come by in life. So, yes. Other questions? Good. So that's a covariant vector, and a contravariant vector is a set of four quantities defined with a lower index rather than an upper index that transform in precisely the opposite way. So in the primed coordinate system, if you think of W mu as a function of the primed coordinates, well, you just get this same lambda matrix multiplied by W in the unprimed coordinates. And it's important to notice that this matrix here is almost but not the same as that matrix here, because I've raised and lowered some indices. And so, for example, you can show, using the transformation rules that I've written down here, that given a covariant and a contravariant vector, v mu and w mu, then their combination, where I sum over the mu indices and where I contract these indices, which is what we call it when we sum over two indices like this, is a scalar. Okay. And so the point is that one can then, starting with vectors and scalars and other sorts of tensors, you can construct even more tensors in sort of the obvious way, where using Einstein summation notation, as long as you're careful to contract only upper and lower indices, you're guaranteed that any tensor operation where you contract indices like this will give you another tensor. So, would you like to see the proof of this? It's quite straightforward. We just use, so for example, v mu, w mu prime, using these prime coordinates. Let's just plug in the definitions. So v mu prime is v alpha lambda mu prime alpha. W mu prime is W beta times lambda mu prime, let's say, lambda mu prime beta. And the question is whether this is equal to V alpha W alpha. And indeed, to show that, we can just use the defining relation for these Lorentz transformation matrices. So lambda mu prime alpha lambda mu prime beta is in fact just delta alpha beta, where delta alpha beta is the Kronecker delta symbol. Namely, it's equal to 1 if alpha is equal to beta and 0 otherwise. And the fact that lambda mu prime alpha lambda mu prime beta is equal to this Kronecker delta symbol just follows from the defining property of these Lorentz transformation matrices that we defined above, namely that this guy is equal to this guy. Okay, so let's just see that in a little bit more detail. So remember that the defining property of a Lorentz transformation was this equation. And so then you could just raise and lower some indices to turn that into this equation. Okay. So in particular, we can rewrite this as lambda mu alpha, lambda mu beta being equal to g alpha beta. All I've done is use the fact that I'm using this g mu nu here to lower that index here. And then I could go ahead and raise the beta index to write this as lambda mu alpha, lambda mu beta equals to, well, let's call it gamma is equal to g alpha beta, g beta gamma. Here I'm just using that inverse metric to raise the beta index and turn it into a gamma. And what is this guy? Well, G was just the matrix 1, let's see, what was it? Minus 1, 1, no, 1, minus 1, minus 1, minus 1. G with upper indices is just the inverse of that, which is, of course, just the matrix itself. And if you think about it, when you multiply those two matrices together, what do you get? You get the identity matrix, delta alpha gamma. Okay, so if all of these tensor manipulations are a little fast, then I recommend strongly that you pay careful attention when you do the problem set this week and try and sort of just get familiar with these operations. There's nothing particularly fancy going on here. It's just a matter of getting used to the notation. Okay. So other examples of vectors and scalars are easy enough to construct. So another example is that given a scalar phi, the set of 4 partial derivatives of phi, denoted d mu phi, is a contravariant vector. That is to say, it is an object, it's a vector with a lower index rather than an upper index. And just as a bit of notation, sometimes we'll call a contravariant vector a one form. How many of you have seen differential forms? Half of you. You don't need to know differential forms. It's just a bit of language. Sometimes I'll call them one forms, and you should know what I'm talking about. So another example of a vector that you all know and love is the electromagnetic field strength. Okay. So in particular, if you assemble the electrostatic potential and the vector potential of electromagnetism into a 4-vector, then if you remember from your electromagnetism class, these quantities transform into one another when one does a Lorentz transformation. And they transform into one another in exactly the way that one needs in order for them to form a 4-vector. That is to say, a covariant vector. And likewise, if I lowered that index using the metric of special relativity, that would be a 1 form. That is to say, a contravariant vector. Now, of course, there are more interesting tensors in the world than just scalars and vectors. And so, in general, we define a tensor of rank n comma m as a set of 4 to the n plus m functions of the coordinates that will denote t with n upper indices and m lower indices, which transforms under Lorentz transformations in such a way that for each upper index it transforms like a vector, and for a covariant vector, and for each lower index it transforms like a contravariant vector. So in some new primed coordinates, for every upper index we get one of these Lorentz transformation matrices. And then for each lower index, we get one of those inverse Lorentz transformation matrices. And here I'm taking advantage of the notation where the primes denote different indices to just make my notation a little bit more compact. And I'm using Einstein summation notation again. So here there are n plus m indices that are going to be summed over. Okay. We will very rarely in this course deal with tensors of rank bigger than 2 or 3. Okay? So it'll be very rare that you have to worry about terribly complicated versions of this formula. And of course, the most famous tensor, well, one of the most famous tensors that you probably have already seen is the electromagnetic field strength tensor. So all of this is a repackaging of the electric and magnetic fields of special relativity. So those electric and magnetic fields are derivatives of the electric and the scalar and vector potentials of electromagnetism. And if we just define their derivatives in this way, then it's relatively easy to check that this is a tensor. And in particular, it's a tensor that is antisymmetric in its two indices. So if I interchange the indices, I'll just get a minus sign. And if you write it out explicitly, this is just the 4x4 matrix that packages together the electric and magnetic fields in a compact way. So here I've just drawn the upper diagonal elements. The ones on the lower triangular region are just given by minus of those on the upper triangle. And as you know, the electric and magnetic fields transform in a complicated way into one another under Lorentz transformations, and that is precisely captured simply by the statement that F mu nu is a rank 0, 2 tensor. And the basic idea of tensors is that because the laws of physics should be independent of coordinate system, the laws of physics must take the form of tensor equations. So, in particular, a tensor equation of the form, say, some particular tensor being equal to 0, that is true in one coordinate system, that is to say, in one Lorentz frame, is then true in all coordinate systems. So, for example, Maxwell's equations take the form d mu F mu nu is equal to 0. So that's a tensor equation. So in particular, you'll check that that gives you half of Maxwell's equations. That's a tensor equation. And the other half of the Maxwell equations all take the form of d mu F nu rho plus various cyclic permutations of this in the three indices is equal to 0. That's another tensor equation. And so because it's equal to 0 in one coordinate system, it's going to be equal to 0 in every coordinate system. Because when you go from one coordinate system to another, you're just multiplying this tensor by a bunch of matrices. Okay. So, for example, if you just stare at it, if you set this tensor equal to, if you set this guy equal to 0 here, then that in the unprimed coordinate system, then that tells you that the guy over here in the primed coordinate system is equal to 0 also. So the laws of physics must take the form of a tensor is equal to 0. So a second example of an equation of motion that would be invariant under the laws of special relativity would be the equation of motion for a scalar. So for example, if phi is a scalar, then the Klein-Gordon equation, box phi is equal to 0, is a tensor equation, so it's consistent with the symmetries of special relativity. In particular, what is that? That's d by dt squared minus the gradient squared of phi is equal to 0, which is just g mu nu d mu d nu of phi is so here d mu is the partial derivative, and d mu d nu contracted with g mu nu, if you think about it for a second, is just this Klein-Gordon operator. So here, again, what you want to keep in mind is that as long as you use Einstein's summation notation, then an object with no free indices is going to be a scalar. So for example, here we have, you take one derivative with respect to d nu of phi to get a vector. You take another with respect to d mu, and you get an index 0, 2 tensor. Then you use this g mu nu to contract those two indices together, you get a scalar. The scalar is a tensor, so that means that if you write down this equation of motion in one coordinate system, it'll be true in every coordinate system. That's why you have seen the Klein-Gordon equation before. It's the wave equation that always appears when you study wave propagation in special relativity, because it's the only quadratic differential operator that you can write down that is consistent, that is invariant under the transformations of special relativity. Okay. So this was just sort of a lightning review of Lorentz transformations. Hopefully most of what I said here was review, probably not every single thing, but most of it. I'd like to now go on and discuss some things that are not review, but before I do, let me pause and see if there are any questions. No questions? Okay. So at various points, as we need more special details about special relativity, we'll introduce them as needed. But I think that should be enough of a review of Lorentz transformations to take us through at least the next little bit. So now I'd like to return to our study of fields, and in particular, before diving into quantum field theory, I'd just like to talk, at least maybe for the rest of this lecture and a little bit of next lecture, about the classical theory of fields. So in particular, we argued that theories of quantum mechanics with multi-particle states must be formulated in terms of systems where you have not a finite number of degrees of freedom, but really one degree of freedom for every point in space. Okay. So the basic question that we'll be trying to ask today is, how can we study in a general way the dynamics of systems with, say, some number of degrees of freedom. It could just be 1 in the case of a simple scalar field, per point in space. Say you could have your degree of freedom phi of x mu, where phi is some scalar field. Or, if you want an example that you're quite familiar with, you should think of the Maxwell field, where you have an electric and magnetic field that are 6 quantities that depend on where you're sitting in space and time. So the most efficient way to package the dynamics of a classical mechanical system is through its Lagrangian. Okay. So just as a reminder, in classical mechanics, the way that we efficiently package the equations of motion of some system is, let's say that we have some finite set of dynamical degrees of freedom qi, where I is an index that runs from 1 up to the number of degrees of freedom you have. Then the way that we describe their motion is by defining an action, which is the integral of some Lagrangian that is some function of the degree of freedom q along with its time derivative. In principle, it could also depend explicitly on time, although for simplicity, in this class we're mostly going to be focusing on cases where we don't have an explicit dependence of that sort. And then the equations of motion are found by imagining minimizing this action as a function of these degrees of freedom, that is to say, as a functional of these degrees of freedom. So you imagine the set of all possible paths through configuration space that this function could take, and the classical trajectories are the ones where this action is minimized or extremized. In particular, you imagine computing the variation of this action as you vary the path through configuration space a little bit. And this is given by the variational derivative, delta S over delta Q. That's just the partial derivative of the Lagrangian with respect to Qi minus the total time derivative of the derivative of the Lagrangian with respect to Qi dot. So setting that equal to 0 gives you the Euler-Lagrange equation that finds the path through configuration space that minimizes this action. And our basic principle for constructing equations of motion and theories of fields that are consistent with the rules of special relativity will be to generalize this procedure to the case where we don't have some finite number of degrees of freedom Qi, but rather now some degrees of freedom that depend both on space and time. Okay. So hopefully this basic formulation of the rules of classical mechanics is familiar to you. If it's not, you probably should go back and review it. Okay. So now in classical field theory, we have some degrees of freedom phi that are functions not just of time, as these Qi's were, but are functions of space-time via the coordinate x mu. And we want to try and formulate our theories in precisely the same way. So we would like to define an action that's a function of your field configuration, that is to say, is a function of the function phi of x mu. And then our equations of motion will be found by demanding that S is extremized in the space of all possible field configurations phi of x mu. So just as in classical mechanics, so in classical mechanics we saw that this is the integral dt of some Lagrangian. So that Lagrangian will depend on your degrees of freedom as well as their first derivatives, just as in classical mechanics. And our theory will be such that when you set the variation of this Lagrangian to 0, in particular you imagine varying our field configuration a little bit and setting the first order variation of your action with respect to that field variation of the field configuration equal to 0, this should give the equation of motion for our field. So, for example, in the simplest case, we would like to find the action which gives the Klein-Gordon equation. Box phi is equal to 0. Or more generally, box phi is equal to minus m squared phi. Okay. Well, the first thing that we see here is that this formula that I've written down where S is an integral dt of a Lagrangian is all well and good, but it certainly doesn't treat space and time on completely equal footing. If you're going to integrate dt, then you should integrate over all of the spatial directions as well. So immediately we see, just by the principles of special relativity, that space and time are treated equally. this Lagrangian should be the integral of some other function that we'll call Lagrangian density. That'll be a function of phi and its first derivative. So that the action is not just a t integral, but an integral d4x. That is to say, an integral over dt as well as over space of this Lagrangian density. So now let's imagine that we have an action that is an integral of some Lagrangian density. And let's ask under what circumstances this action is going to be minimized or extremized in the space of all possible field configurations. So how do we determine when this action is going to be extremized? Well, we imagine that we start with some field configuration phi. That's going to be some function of x. And we vary it slightly by adding to it some small variation that I'll call delta phi. And then let's ask how this action S will vary to linear order in this small variation delta phi. So S will go to S plus delta S. And now let's go ahead and compute what delta S is. So to first order in this variation delta phi, what's delta S going to be? Well, S was an integral d4x, so delta S will be an integral d4x. And now we have to ask how this Lagrangian changes as we vary phi. Well, the Lagrangian depends on both phi and the first derivative of phi. So we just go ahead and use the chain rule. So as phi goes to phi plus delta phi, there's one term that comes from the dependence of L on phi. That's just dl by d phi times delta phi. And another term that comes from the dependence of dl on the first derivative of phi. So what is the variation of the first derivative of phi? Well, phi is going to phi plus delta phi. So that means that d mu phi is going to d mu phi plus d mu of delta phi. So delta of d mu phi is d mu of delta phi. So those are equal. So the variation of the action is d4x times dl by d phi delta phi plus dl by the derivative with respect to d mu phi of d mu delta phi. Okay. Yes?
Is that L supposed to be the other kind of L?
Oh, sorry. Yeah. That's supposed to be the L. Okay, good. Thank you. Sorry about that. Yes, it's the Lagrangian density. Yes, I was a little sloppy about how curly my L's were. Okay. Good. Any other questions? Good. Yes, this L is the Lagrangian density here. I'll probably just make it messier if I try and make all of these things curly. Oh, that's not so bad. Okay, good. Thank you. So now what I'm going to do is I'm going to take this term and integrate it by parts. So this is the integral d4x of delta phi times dl by d phi minus the derivative of dl by d mu phi plus a total derivative term So for those of you who remember the derivation of the Euler-Lagrange equations from classical mechanics, these manipulations should be very familiar to you. So now we want to do two things. The first thing that we want to do is think about the sorts of field variations that we're considering. So the first thing that I'm going to do is I'm going to imagine that we're considering a variation of our field configuration phi such that delta phi vanishes sufficiently quickly at infinity. Okay. Why do I do that? Well, this term here is the integral of a total derivative. In a space without a boundary, the integral of a total derivative is just equal to 0. But of course, space, you could worry that there would be some boundary term that would arise here at x mu, the absolute value of x mu being very, very large, large T or large space. But I'm just going to demand that my field configurations vanish out at infinity, so that this term is just equal to 0 by Stokes' theorem. So Stokes' theorem says that the integral d4x d mu of j mu is equal to 0 if j mu vanishes out at infinity. And now the second thing that I want to do is I want to demand that this variation of the action should be equal to 0 for arbitrary field variation delta phi that vanishes sufficiently quickly at infinity. So delta s over delta phi, the variational derivative of s, is simply defined to be this guy in the quantity inside the parentheses here. So that's dl by d phi minus the gradient of dl by, or of, sorry, I guess it's the dot product. Is that what it's called? Yeah. I guess you would call it divergence in vector calculus. So it's d mu of the derivative of L with respect to d mu phi. So this should be equal to 0 in order for S to be extremized. And these then are the Euler-Lagrange equations that determine the dynamics of a classical field given the action of the field in classical field theory. Okay. Are there any questions on this derivation? Yes.
Is the L supposed to be the curly L?
Yes, this is all curly L. Curly L. Yes. Thank you.
Then how does that get rid of all the integrals?
Well, okay. The point is that this variation of the action is supposed to be 0 for arbitrary function delta phi. Okay. And so the integral d4x of an arbitrary function times this guy in the parentheses here is equal to 0 only if that quantity in the parentheses is equal to 0. Okay. So, and then, yeah, okay. I define delta s over delta phi to be the thing without this d4x here. That's just my definition of a variational derivative. It's the difference between a variational derivative and a normal derivative. The variational derivative of a functional with respect to a function is a function, not a number. So that means I have to remove that integral. You should think about this as being analogous to a gradient. Okay. So for example, you should compare this to the expression in standard classical mechanics, where you imagine that you have some number of degrees of freedom labeled by some index qi, so that's dl by dqi minus d by dt of dl by dqi dot. Okay. And here, you imagine going from this equation to this equation by making the replacement where that I, so previously in classical mechanics, I is an index that labels the degrees of freedom. In this equation, you want to think of your spatial position as an index that labels the degree of freedom. Qi goes over to phi of x. Good. Yes?
When we place
Yes.
Is this always the case?
Yes. So what do you mean by delta of d mu phi? What we mean by delta of d mu phi is the amount that d mu phi changes to linear order in delta phi if phi goes to phi plus delta phi. So phi is some function. Delta phi is another function. It's a small function. Put a little epsilon out front of it, and then work to linear order in epsilon. If phi goes to phi plus delta phi, then how does the derivative of phi change? Well, the derivative of phi goes to the derivative of phi plus the derivative of delta phi. Okay. So when we say delta of d phi, we mean the amount that d phi changes when we do this small variation of phi. Okay.
But if the coordinates also change,
We're not doing a change of coordinates here. Okay, there are special, so in a few minutes we'll consider the special, you could choose, for example, d phi coming from some change of coordinates, that's some special choice, okay. And then you would have to think about this a little carefully, but we're not changing the coordinates here. We're not changing x mu to x mu, times whatever. We're imagining just a variation of your field. In the same way that, when you study classical dynamics, you imagine an arbitrary, the action as a function of the path that your system takes through configuration space. And then you minimize it as a function of that path. Good question. Good question. Any other questions? Okay. So then, let's now imagine if you had a theory with more than one field, then you simply generalize this in the natural way. Okay. So if you have, say, a bunch of fields, let's call them phi I, where I is an index that labels the fields, then you'll characterize the dynamics by some action that's a functional of these various fields. And then the equations of motion will just say that the variational derivative of S with respect to phi I must be equal to 0 for each value of I. So let's try and work out a couple specific examples of this. So the simplest example will be that of a single scalar field. And what sort of action should we write down? Well, it should be the integral d4x of some Lagrangian. And in classical mechanics, the kinetic term in a Lagrangian was something quadratic in the derivatives of phi, so of the dynamical variable. So the typical Lagrangian for some particle would be x dot squared. Okay. So the natural generalization of that would be some quantity that's quadratic in the derivative of phi. So it should look like something like d mu phi, d nu phi. In order to be consistent with special relativity, this better be a scalar. The only scalar that you can construct is g mu nu, d mu phi, d nu phi. And, well, that's not the only scalar. That's the only scalar that you could construct that's quadratic in derivatives of phi. You could also, if you wanted to construct a scalar, imagine adding to that some arbitrary function of phi. So this is the most general scalar that you could imagine writing down, okay, which would give you, it needs to be a scalar in order for the theory to be consistent with special relativity. And then what's the equation of motion? So this is the derivative of the action with respect to phi minus the derivative of the action with respect, here, just to make everything a little clearer, I won't repeat my indices here. So what is this Euler-Lagrange equation? Well, for this Lagrangian, dl by d phi is just minus v prime, the derivative of v with respect to phi. and then minus d by d alpha of the derivative of the Lagrangian with respect to the derivative of alpha. And if you think about it for a second, that's just g mu alpha d mu phi with no 1/2, okay? Because there are two terms. There's the first term where you take the derivative of this guy with respect to d phi, and the term where you take the derivative of this guy with respect to d phi. That's why I put that 1/2 out there to begin with. Okay. Because, so, you know, you should think in your head about the comparison with classical mechanics, where the Lagrangian was 1/2 q dot squared minus v. Okay. Then the variation of the action with respect to q, what is that? Well, there's minus v prime of q minus d by dt of q dot. Okay, because the derivative of 1/2 q dot squared with respect to q dot is q dot. Okay. And so all I've done is the same thing here, and we can write this a little more succinctly as minus d mu phi minus v of phi being equal to 0. And indeed, this is our old friend, the Klein-Gordon operator. It's the only operator that you can get that gives you a second-order wave equation consistent with the rules of special relativity. And so, for example, if this function v is quadratic in phi, then this gives the Klein-Gordon equation. d mu phi is equal to minus m squared phi. So the action that I wrote down up here is a generalization of the action describing a Klein-Gordon field to a more complicated set of theories where this phi appearing on the right-hand side of the Klein-Gordon equation was replaced by a more complicated function of phi. It was replaced by v prime of phi. Any questions on that? So if this manipulation here, where I went from here to here, or from here to here, was a little fast, I encourage you to go through it all out completely explicitly. Sometimes things can get a little fast using the index notation, so just write it all out. If it's confusing, write it all out without any indices. Write out the t's and x's explicitly, and you'll check, and it'll all become clear. Any questions? Was that too fast? Was it too slow? Was it just right? Okay. I should make one comment. Okay. So, typically, at least initially in this class, I'm going to restrict to theories where the Lagrangian depends only on phi and its first derivative. Okay. And moreover, I'll restrict to those theories which are quadratic in the derivatives of phi. In that case, the only sorts of kinetic terms I could write down, that is to say the only sorts of terms that I could write down that depend on d mu phi, are terms of the form d mu phi times d mu phi d nu phi g mu nu. Those are the only scalar terms that I could write down to give equations consistent with special relativity. But later on in this course, when we discuss effective field theory, we will need to consider more general functions. Where you might have dependence on more derivatives, higher derivatives of phi, or where you might have higher powers of single derivatives of phi. We will consider those, but these theories are actually rather tricky and rather delicate to study quantum mechanically. And so because all of the simplest theories are things like the Klein-Gordon equation, so for example, electromagnetism and quantum electrodynamics are described by essentially simple generalizations of the Klein-Gordon equation with these simple sort of kinetic terms. I'm not going to start out by considering these more complicated theories. So for now, we'll focus on theories where you only have two derivatives of phi in the action. Okay. So a second set of examples would be the example of electromagnetism. So you can think of electromagnetism as a field theory where you have four fields that are these electromagnetic field strengths, A mu. Now, you can ask what sort of scalar can you construct from first derivatives of A mu. Okay. Well, we already saw that F mu nu, which was the antisymmetric combination of first derivatives of A mu, was a 2, 0, 2 tensor. Okay. So if you want to construct a scalar out of that, well, you need to start contracting indices. And if you think about it, this is the only thing that you could construct that is quadratic in the A's and quadratic in their derivatives. So this is the only possible scalar action that you could construct that is consistent with the rules of special relativity, that is to say, is a Lorentz scalar. And so because of that, you won't be too surprised to see that if you study the classical equations of motion coming from this action, this gives Maxwell's equations. So that's something that you'll prove on a problem set. Not this week. I thought you had, the problem set I wrote was long enough this week. In particular, the variation of the action with respect to A mu gives you this half of Maxwell's equations. So here I'll make my indices consistent. So nu is my free index. So that gives half of Maxwell's equations, and the other half of Maxwell's equations follow automatically from this equation here. And that's something that you will show in this week's problem set. Okay. So we've seen the basic formulation of the dynamics of some classical theory of fields, formulated as the minimization of some action regarded as a function of the set of field configurations. Before we go ahead and try and quantize this system, which is what we're going to do, I'd just like to spend a little bit more time talking about the roles of symmetries in classical field theory. Before I do so, let me pause and see if there are any questions.
That's the equation in free space, right? That's the
Equation in
free space?
free space?
I mean,
Sorry.
there's no charge or...
Yes, so yes. So for example, if you wanted to generalize this, as you will on the problem set this week, okay, to current, then you would put a current 4 vector there. Yeah. Good. Question? Yes. Is there a reason why it's antisymmetric? Well, yes, there are many reasons why it's antisymmetric. Okay. Well, let's put it this way. Let's say that you want to, so first of all, that quantity is not a tensor. In order to construct a tensor, I need to be a little careful. But, I mean, that quantity is a tensor in special relativity, but not in general relativity. Okay. So, there are various ways of explaining why you need to have that there that I don't necessarily want to go into. Okay. One of which is that if you want to formulate a theory only in terms of differential forms, so if you think about the theory of differential forms, then a differential form being a fancy name for a tensor with only lower indices that's completely antisymmetric, then this is the natural thing that you construct when you think of the theory of differential forms. But let's not go into that. Okay. So is there a reason? I mean, sure, there's a reason. I mean, if you want a very prosaic reason, you want something that, yeah, okay. So let's not try and go into that. There are plenty. There are reasons, but yeah. I mean, this is a very geometrical formula. Okay. In some sense, taking the antisymmetric combination is the most natural way of taking a derivative of a one form, and not doing it would be a very unnatural thing to do. Okay. If you want to think about it, this is the, yeah, let's not go into that. I was debating whether or not to give you an introduction to the theory of differential forms as well, but that seemed to be aside from the main thrust of this course, so I decided not to. Yes. But electromagnetism and gauge theories are much more beautiful and easy to think about when you think about them in that language. Okay. I don't think that's something that we'll probably do in this course, though. Yeah. Okay, other questions? Okay. So let's talk a little bit about symmetries. Okay. So a symmetry is some sort of transformation, that is to say, some sort of rule, which, given some field configuration phi, allows you to construct some new field configuration phi prime that's some function of the original field configuration that leaves the equations of motion unchanged. And in particular, because the equations of motion are found by minimizing an action, we'll be interested in symmetries that leave the action unchanged. So symmetries come in two flavors. There are discrete symmetries and continuous symmetries. A discrete symmetry is something like a reflection symmetry, say if you take x to minus x or t to minus t. And those are useful, but much more useful are continuous symmetries. So a continuous symmetry is a family of symmetries, that is to say, a family of transformations that depend continuously on some sort of parameter alpha, such that when alpha is equal to 0, you get the trivial symmetry, namely the one that doesn't do anything to the field. So that if you imagine the transformation phi going to phi prime as a function of alpha, you could expand order by order in alpha and consider only the small symmetry where alpha is taken to be infinitesimally small, and you work at linear order in alpha. So what we have here is a set of symmetries that depend on this parameter alpha. And by definition, for every value of alpha, the action is unchanged, so that delta S is equal to 0. So delta S is equal to 0 for all alpha. So in particular, we could work at linear order in alpha and ask what the variation of the action is. Okay. So in fact, we just calculated the variation of the action for an arbitrary transformation delta phi. So delta S being equal to 0, to linear order in alpha, we can then ask what that means for the dynamics of this field phi. So in particular, so the first thing that we want to note is that if delta S is equal to 0, that does not mean that delta L is equal to 0. Because S is the integral d4x of 0, d4x of L. So that implies not that delta L is equal to 0, but instead that delta L is a total derivative. So I'll call it d mu of q mu. So if delta L is d mu of q mu, then delta S is equal to 0. So by the definition of a symmetry, we know that to linear order in alpha, delta L is going to be some sort of total derivative. But we could also go ahead and compute delta L directly. So what is delta L? Well, this is what we did on the previous, just 10 minutes ago. It's delta phi times the equations of motion, okay, plus that term that we discarded, which was a total derivative. So let's go ahead and remind ourselves of what that term was, plus this term here. Okay. So it was plus the total derivative of dl by d of d mu phi times delta phi. So setting these two things equal to each other means that there's some vector that I'll call j mu, which is equal to dl over d mu phi times delta phi minus q mu, which has the property that d mu of j mu is equal to 0. So what do we conclude here? What we conclude is that if we have a continuous symmetry, under which phi goes to phi plus alpha delta phi plus higher order in alpha, then by the definition of a symmetry, that means that L goes to L plus alpha times d mu q mu for some vector q mu. Then we can construct the quantity j mu defined by this equation, and then it will obey this boxed equation where its divergence is equal to 0. So we have a special name for vectors that obey this equation, that d mu of j mu is equal to 0. They're called conserved currents. So why are these quantities useful? Well, they lead to constants of motion. So, for example, let's consider the following. So let's consider, I don't want to call it Q. Okay, let's consider the following quantity E, which is the integral d3x of j0 for some conserved current. So if you have a symmetry, then that guarantees you the existence of one of these vectors that obeys this conservation law, d mu j mu is equal to 0. So then let's consider the time derivative of E. What is that? That's the integral d3x of the time derivative of J0, which using the conservation rule, so d mu j mu is equal to 0, that's the same as J0 dot minus del dot j. And then this, provided j falls off sufficiently quickly at infinity, will be equal to 0 by Stokes' theorem. So that means that whenever you have a continuous symmetry, you have a conserved quantity. That is to say, a constant of motion. Just to reiterate, whenever you have a continuous symmetry, for every solution to the equations of motion, you can compute this conserved current J. Its divergence will be equal to 0, which means that the spatial integral of its 0th component is a constant of motion. So hopefully this general set of ideas is familiar to you from classical mechanics, because this is nothing more, nothing less than Noether's theorem, in a field theory. You guys have all seen Noether's theorem, I hope? In particular, this is the usual relationship between symmetries and conserved quantities. Questions on that? So let me just do a simple example. Maybe before I do this, even before I do this example, I should just mention that this can be generalized to the case where you have multiple fields. And in that case, let's say we have multiple fields labeled by an index I. All you need to do here is sum over I. Okay? So again, I'm using Einstein summation notation. So if that's not obvious, then go through the derivation again and convince yourselves of it. So let's consider a simple example. And this is a nice example because we'll meet a new field theory. So let's consider a theory of a scalar field. But instead of considering a real scalar field, so that phi is some Hermitian operator in the quantization of the theory, consider a complex scalar field. So this is a theory where we don't have one real degree of freedom per point, but we have 2 degrees of freedom per point, the real and imaginary parts of phi. And I would like my action to not only be a Lorentz scalar, but I would like it to be real. That's for reasons that will become clear later on. That's because So my action I'm going to take to be d mu phi star d mu phi minus m squared phi star phi. That's just a simple example. So because I chose my action to be real, this guy has a symmetry where phi goes to e to the I alpha phi. So at linear order, this means that delta phi is equal to I alpha phi. And the complex conjugate phi star goes to e to the minus I alpha phi star. So delta phi star is equal to minus I alpha phi star. So you can then go ahead and write down the conserved current. So I'm out of time here, so I'll just write down the answer for you. So So J mu is dl by d mu phi times delta phi. And if you want, so, and here we really should think of this as a theory where I have two fields, the real and imaginary part of phi, and I need to sum over them separately. And if you go through and work it out, this is just minus I times phi d mu phi star minus phi star d mu phi. Okay. And then you could go ahead and work out the equations of motion and check that for solutions of the equations of motion, which turn out just to be the Klein-Gordon equation, so grad mu phi, grad mu d mu phi is minus m squared phi. Indeed, we have that d mu j mu is equal to 0. So I introduced this example because hopefully this current is at least a little bit familiar to you. So this should remind you of quantum mechanics. So in quantum mechanics, if you have a wave function psi, then you can define the probability current, which is psi star grad psi minus complex conjugate. And that is also conserved in quantum mechanics. You can think of this as three components of a conserved 4 vector whose 0th component is the probability density. Or the time, yeah. Psi star psi dot minus complex conjugate. So the probability current in time. Now here, of course, we're talking about a classical field theory. And so phi and phi star are not the wave function of a quantum mechanical theory, but just the classical degrees of freedom of some theory. But again, we're seeing that there's some conserved current. And in fact, as will become apparent later on in this class, this particular example that I brought up is an important and an interesting one, because this is really basically how one would describe a field that carries charge, a particle that carries charge in quantum field theory. You would describe it in terms of a complex field of this sort. Okay, so let me stop here unless there are any questions. Okay, I will see you all on Tuesday. My advice is do not leave the problem set for the last minute. I would strongly encourage you to not do that. Yes. And again, if anyone who has not sent me their email address, please do so unless you're registered for this course, because I'll be sending out some email announcement presumably at some point. Yes, question in the back. Oh, I'm sorry. Yeah, you're right. Good. Thank you. Good.